Hi, everyone. Today, we are very happy to have Mukund Rangamani from UCDavis give us a talk about open quantum systems with memory from holography. Thank you so much for accepting to give a talk. Please.
Thanks, Nima, and thanks, everyone, for having me to speak. I'll talk about some work I've been doing in the past almost 2 years now with various people, which I'll mention in a bit. And the idea is to try to leverage what we know about holography and strongly coupled systems to write down effective field theories for open quantum systems. So I'll explain what we are after and what we have achieved so far in the course of the talk. So rough set of references. This is mostly work I've been doing with my longtime collaborator, Logan Igam, and various students and postdocs. So we laid out a broad strategy for how we can use holography for this purpose almost 2 years ago in a paper with his student, Chandan. And then we've been systematically trying to study various examples, trying to understand diffusive dynamics and propagation of sound with various other collaborators. I would like to highlight some of our postdocs, Temple Hay, who's been with us for a few years and is going to Caltech, and Julio Virueta, who came to us about a year and a half ago from Stony Brook. So let me motivate the problem as follows. So we're going to talk about a quantum system, which I'm going to think of as having two components, one which I'm going to call an environment, and the other I'm going to call a probe. So I'll typically denote the environment degrees of freedom by X and the probe degrees of freedom by some psi. And we will posit that the joint environment probe system as a quantum system evolves unitarily. So there's a natural quantum mechanical description where the state operator of system tensor environment has some nice evolution, but we're not interested in asking what's happening in detail to the environment. We're happy to trace out the environment and ask what the probe dynamics is. So in other words, if I have the density operator on system and environment tensor probe, if I trace out the environment, I get the reduced operator on the probe system, and the probe system by itself evolves via a non-unitary quantum channel. So because this is lossy, we're forgetting about what the environment is doing, and the probe evolution is described by some map, which we hope is a completely positive trace preserving map from the initial probe density matrix to the evolved probe density matrix. And what we're after is what is the effective field theory in a quantum field theoretic sense of such quantum channels. Okay? There are many open questions in this area, and what I'll try to convince you is that the broad scheme of this program is well understood dating back 50, 60 years, but the quantum field theoretic aspects, especially how renormalizations work, how effective Lagrangians are written down, is something that has been not fully answered, and I think holography gives us a pathway into addressing those. So the primary prototype for this goes back nearly 6 decades, and it was laid out in a nice paper by Feynman and Vernon. So we have a evolution of system of our probe, which have times the environment, which has a nice path integral description. I'm sort of cheating here because what I should really have written here is the density operator for probe tensor environment, but I've just written the path integral for just the state operator for the case, just the evolution. I just trotterized the exponentiated the uniter that evolves the system tensor environment. And I'm tracing out here these X degrees of freedom. So I'm completing the path integral over X. But since what remains in the probe is not a pure state, it's a density operator, I have to keep track of both the bra and the ket pieces of the density operator. So the way I'm going to do that is going to tell you that we'll keep track of 2 copies of our probe degrees of freedom, which I'll call right and left respectively. And these are the right you can think of as proxy for kets and the left as proxy for bras. And you see that in the action, there's a piece which is e to the I psi right and e to the minus s psi left. So the action for the right evolves forward, and the action for the left degrees of freedom evolves backwards. The minus sign indicates that this is the anti-unitary evolution of Okay, brass. The crucial point, and the point that Feynman and Vernon emphasized very emphatically in their paper, is that once you've integrated out the environment, you're no longer guaranteed that the right and left, the brass and kets, it's not just a simple product projecting density matrix. Rather, you have some non-trivial interaction between the brass and the ket degrees of freedom. And they gave a name to this quantity. They call this the influence functional. And related to what I said earlier, for this to a good quantum channel, this influence functional must have some sign definite properties. So in particular, the system is lossy, so this influence functional has frictional terms, so it's not purely real. It has imaginary pieces. It's not a pure phase, as it would be for a Lorentzian quantum field theory. But the imaginary pieces need to be sign constrained for the operation of tracing out for this all for the probe system to evolve unitarily, to evolve as a quantum channel, the evolve unitarily. And our guideline is really that this influence phase should be constrained by the microscopic unitarity of system tensor environment. Okay. So here's a simple prototype. This prototype was mentioned already in this paper, but it was beautifully solved in a nice example, which goes by the name of quantum Brownian motion by Caldera and Leggett in '83. And it has really been a sort of go-to example for much of the discussion of open quantum systems. So it's a very simple quantum mechanical model. It's Gaussian, so we can just calculate through and through. So the environment, so the probe is taken to be a single free particle with some mass m. So the analogy is it's a Brownian particle in a medium, and we want to understand its quantum dynamics, not the classical Langevin dynamics, but we'll see where the classical Langevin type dynamics emerges from. The environment is modeled as a bath of oscillators, large number of oscillators, which are in a thermal state. And the coupling is taken to be some simple linear coupling between the probe degrees of freedom Q and the environment degrees of freedom X. Okay, I initialize the system in the thermal density matrix of the environment, tensor the pure ground state of the probe. And then I say, go through, carry out the path integral, integrate out the environment, and ask what the effective dynamics of the probe is. Okay. So as I said, this is a Gaussian problem, so we can just finish the path integral. It's a reasonably straightforward exercise. But there's a beautiful story that you can tell of what the effective probe dynamics is. And the effective probe dynamics is that of a quantum Brownian particle, where its motion is governed by the usual kinetic term for a free particle. So, but now, because it's interacting with the environment, it's getting buffeted, and therefore there is some friction or dissipation into the medium with some friction coefficient gamma, and stochastic noise, which tells you some random force acting on this particle. Okay. So just as you would understand this story in kinetic theory for Brownian motion, this is the same thing where instead of a Brownian particle, you have a probe free particle interacting in a bath of oscillators. And in this model, one can check microscopic unitarity tells you something important. It tells you that the noise spectrum of this fluctuation is related to the friction or dissipation coefficient by the standard fluctuation dissipation, or in this case, Einstein Somoluchowski relation. Okay. So this is the effective classical stochastic description after integrating out the environment. But you might ask a separate question, which is more interesting from a field theory point of view, which is what is the effective probe dynamics? What is the effective action for the probe dynamics having integrated out the environment?
Mukund?
Yeah.
And in this problem, don't you need to assume, I mean, I'm a little bit confused about the intuition here. Don't you need to assume that environment is infinitely large or something?
Yes, you need to assume thermodynamic limit to get this answer.
I see. So somehow the dimensionality of the Hilbert space of the environment over the dimensionality of this Q variable has been taken to infinity to get this approximation. I see.
Yes, except that I will say one caveat, that when you actually describe just the probe effective field theory, by monogamy of entanglement, you don't need to know how big your environment was. in the sense that it's sufficient to have a double set of degrees of freedom to describe the probe density matrices evolution.
But I mean, if your, I'm just confused, if your environment is finite dimensional, there will be recurrences, so there will never be true dissipation.
That is true. That is true. So yes, but I'm saying that, you know, that there's some order of limits issue here. But I'm saying the action. So here I would have some recurrences coming from the fact that there would be true thermodynamic limit in my various coefficients.
Right. One more question about this. So don't we need also a second assumption, which is sort of like a memory-less assumption, that the time scale of interaction with the environment versus the internal time scale of the system is an order of parameters?
Great. Indeed, this is very good, because I'm going to say something about memory-less systems with memory in a while.
Okay.
This system is assumed, this calculation was done assuming a Markovian assumption that the environment sort of thermalizes quickly and the probe particle forgets where it started from. Yes.
Sorry, how do you break time reversal then? You do some assumption.
Sorry?
How do you break the time reversal?
You break time reversal because you have dissipation in this problem.
But you have to choose the dissipation, the sign, or
no. So what I'm saying, what I will tell you later, and this is important, and I don't know how to prove this in general. In this problem, you can check what is the sign. The sign comes from the fact that the probe system talks to retarded response. It doesn't talk to advanced response. So in some sense, this is like the physics of friction, not anti-friction. And the sign comes from an underlying statement of second law, which is coming from positivity of this quantum channel.
So you need to assume second law, I guess.
In this calculation, I think yes, but I would hope that in general, one should be able to prove that quantum channels obtained by integrating out environments are positive maps.
But sorry, quantum channel by definition is a positive map.
No, quantum channel by definition is a positive map, agreed, Nima, but I'm saying that I don't know how proof that, maybe I should have said it better, that in general, integrating on environments lead to quantum channels.
But okay, maybe we could discuss this offline, but I thought also, okay.
So let me outline for you what the effective field theory is. So the effective field theory is, which governs this Brownian motion, is given by two sets of degrees of freedom, which I will call the right and left. And I'll write them in a particular way. I'll write the dynamics in terms of linear combination of light and left degrees of freedom, what I'll call average and difference variables. And here is the quantum Lagrangian, which, as you see, includes an imaginary piece, which comes from the fluctuations, and includes some coupling between the right and left coming from the fact that there is non-trivial interaction and friction in the system. So this action, you can obtain many different ways. The fastest way to obtain it, which is how these folks, Martin, C. Jan, Rose, for example, obtained it, is by taking this Lagrangian, this equation of motion, implementing a Lagrange multiplier, degree of freedom, to give you the equation of motion, and then exponentiating that to write down in the usual Fourier-Popoff BRST sense to get an action. But I claim that you don't have, in this particular problem, you don't have to do this. This is something you can just do by working out how the density matrix evolves, the path integral level. In Kenneth matter literature, this average degree of freedom is usually called classical, because this is really the Q variable that enters in the stochastic description. And the difference variable is called quantum because it controls the noise or the fluctuations about this classical stochastic motion. Okay, so you see that there is a structure here, which I will use later, and that structure is deeply constrained by the fluctuation dissipation relation, and signs are constrained by the fluctuation dissipation relation. So if you have non-Gaussian, so the environment I picked was Gaussian. It didn't have anything non-Gaussian. But if you want to do quantum mechanical analysis for non-Gaussian environments, one can actually go through the exercise, and this was done a few years ago by these folks, and they derived a general effective field theory for such probe dynamics, including signatures of what out-of-time ordered observables would be in such effective stochastic models. A better way to say it, which is related to Nima's question, is that when you can assume that your environments have short-term, have interactions that don't live for a long time, and the interaction between the system and environment, your probe and environment is short-lived, and the probe forgets its initial state, which I will call the Markovian approximation, then the 1pi effective action of probes is basically easy to obtain. You can think of the system, the environment action, the probe action, and you can think of the probe environment couplings as follows. The effective field theory of the probe is governed by coefficients which are correlation functions of operators of the environment. Because this is just some linear coupling at linear order, it's just some coupling Q times some operator built out of the environment degrees of freedom. So you could just compute, if you want to write down the effective field theory, you can write down, say, non-Gaussian term Q cubed, that corresponds to computing a 3-point function in the environment theory. Which 3-point function depends on which couplings you're trying to compute. So if you're trying to compute this average difference correlate coupling, that corresponds to retarded response, whereas if you're trying to compute difference coupling, it corresponds to the symmetrized correlator or the fluctuation in the environment. So what I want to convince you is that a similar story ought to exist for quantum field theory, except that there is no clean statement from the point of view of deriving such a thing for perturbative quantum fields. And the reason has to do with the issue that Nima brought up, that if you have perturbative quantum fields, the interaction timescales are long. Thermalization timescales in perturbation theory are very, very long. They scale at least inversely with couplings. This means that any probe that interacts with the environment is slow to scramble, and you have to keep track of what the environment is doing for very long periods of time before you can integrate it out. This leads to various issues in trying to compute this problem in perturbative dynamics, and various people who've attempted this end up with various spurious singularities and UV divergences, which don't seem to have any physical origin. So I'm going to circumvent that whole discussion by saying, let me start the problem by looking at environments which are maximally scrambling. Even there, I'll show you the issues. But for now, let me start with holographic environments where I can make strong statements about being able to integrate out the environment which has fast interacting timescales. Okay. So the kind of problem I want you to keep in mind, this is a simpler quantum mechanical problem, which I want you to sort of have in mind as an analogy. The simpler quantum mechanical problem is basically model in holography, the same problem we just started discussing. The problem of Brownian motion in a thermal plasma. So this you can easily do, and some of us argued how to consider this in the context of ADS-CFT almost 15 years ago. And what you do is you look at the dynamics of a probe quark in, say, thermal n equals 4 super Yang-Mills plasma, where the plasma is strongly coupled. And the dynamics of a probe quark qualitatively is as follows. The quark, being a probe, has a flux tube attached to it. And that flux tube in the gravitational description is described by a classical string solution. This classical string flux tube dangles down and dangles into the horizon of the dual black hole that corresponds to the holographic dual of the thermal plasma. This string which dangles down into the black hole, it sort of interacts with the black hole's thermal atmosphere. And the qualitative picture is actually quite nice. It just, you look at the induced geometry of this world sheet, and the induced geometry is a 2D black hole. And the thermal fluctuations coming from this horizon, which is world sheet Hawking quanta, they are the fluctuations that give you this quantum noise, whereas the dissipation is basically arising from the standard way dissipation arises in black hole physics through quasinormal modes. Okay, so this was employed by various people to understand effective field theories in this setup. So there was some work in about 10 years ago, but there's been some new recent progress in trying to derive this problem, derive this effective action systematically using real-time holography. I particularly highlight this paper from a couple of years ago, which inspired me to relook at this problem in quantum field theory. So that's the statement at the level of quantum mechanics. So now everything else I'm going to say is at the level of quantum field theory. And here's the example I want you to keep in mind. We'll take, for example, a d-dimensional probe coupled to a d-dimensional holographic thermal conformal field theory. So if you want to be very specific, you can consider n equals 4 sup Yang-Mills, 4-dimensional field theory. That will be my environment at finite temperature. And I'll just pick linear couplings between my probe psi and the environment, and I'll model the environment degrees of freedom which are coupled as in terms of some gauge invariant single trace operator. Okay, so that's a setup. And my claim is, if I'm integrating out the x degrees of freedom, the effective action for psi cares about correlation functions of OX. It cares about real-time correlation functions of OX, both retarded response and fluctuations around it in a thermal medium. Okay, so our problem is actually quite straightforward. We can constrain this very straightforwardly by working it out by computing real-time correlation functions. So we need a dictionary to compute real-time correlation functions of thermal systems in holography. So that's mostly what I'm going to describe, but I can translate those calculations into this effective field theory, as I'll show you. You can think of this construction in the language that was outlined by Faulkner and Polchinski as a semi-holographic picture, where you have a holographic environment and a non-holographic probe. So you can use the non-holographic probe, and the dynamics of the holographic environment is imprinted onto this non-holographic probe. So, and as I said, the data needed is just these real-time correlators, and various people have studied this, but I'm going to use a particular story that was outlined a couple of years ago by our friends from MIT, Hong Liu and his students, former students, Michael Crossley and Paolo Glorioso.
Mukund?
Yeah?
Can I ask a very naive question? Sorry, I want to ask it before you get into the details of this. So
yeah.
if I'm naive and I don't really know much about holography, and I want to like do this in just CFTs, right?
Yeah.
Like sort of and use conformal field theory techniques to see if I can do something. Is there some sort of a quench problem that we're studying? We're introducing some degrees of freedom that we couple to quantum field theory. And what would be the meaning of some sort of effective action?
Yeah, so we can phrase the problem in 2D, let's say, where it's much simpler to say and answer what you're asking. You just take any conformal field theory, and let's say you have a probe scalar field for sake of discussion, and you couple the scalar field to some scalar operator of the conformal field theory.
Right.
Okay, so you think of the scalar as some kind of probe. So it's like, you have some plasma and you want to have some readout of features of the plasma. So it's like I'm sticking a thermometer into the plasma. I don't need to know what the details of the plasma are. So I need to know what the effective dynamics on the probe is.
Right.
So that's what you would do. And if you're trying to do that, if you couple your scalar with, say, some operator, let's pick Ising model and couple some scalar with some disorder operator, say.
Right. Okay. Thank you.
Then you would pick up some correlators of the disorder operator, and those would, but you'd have to compute the real-time correlators in the CFT.
Correct. Thank you.
So in 2D, you can pretty much get low point functions by taking the known answers on the plane or the cylinder and analytically continuing them.
Right.
Okay, and I'll show you that agrees with holography, as I'll show you in some. I won't give you equations, but I'll convince you. I'll just tell you qualitatively that that's not a surprise.
Thank you.
So I don't want to get into a lot of detail here, but I want to tell you how to do real-time correlation functions without using Euclidean answers and analytic continuation. So the standard field theoretic way of doing them is to actually do the following. So the environment. So now the discussion is all about the environment. Okay. So whatever I'm going to say is about computing correlation functions in this environment, in this thermal environment. So I have a thermal state. That's rho beta. And I want to compute correlation functions of Heisenberg operators. Right now, they have some Lorentzian time ordering, but I'm not going to compute all correlators of these Heisenberg operators. I'm only going to compute a certain set of out-of-time ordered correlators. And those are the ones that can be computed on what I call the Schwinger-Keldysh contour. So Schwinger-Keldysh contour you can think of as follows. There's in the past, at some early time, you have your density operator. There's a ket piece of the operator that evolves forward. There's a bra piece of the operator that evolves backward. And you get to insert these operators at various times. This is Lorentzian time. And once you've inserted operators till the latest time of interest, to the largest time you're going to probe the system with, you identify the bra and ket forward-backward evolutions. So in other words, the trace you can think of as a projection against the maximally entangled state in the far future. And in the past, you have a density operator. And this is just the technical expression of what correlation function we're computing. If I just wrote down this trace, these would be the correlators I would compute. And what I want here, which is related to some of the earlier questions, is I want to compute suitable retarded responses, which are computed by expectation values of commutators with theta functions to indicate time ordering, and expectation values of nested anti-commutators, which actually correspond to fluctuations associated with those thermal correlators. Okay. So the question that these folks gave an answer to, and as had other people, but this is the cleanest answer that I know of in the literature so far, is if I give you such a boundary imaginary time contour, what do you do in gravity to compute correlation functions in holography? So this contour is an imaginary time contour in the boundary field theory. So the usual rules of ADS-CFT say, take this contour and fill it in with a bulk geometry that has the right character, that has this contour as the asymptotic boundary. So if we were just doing the Euclidean problem, there would be an imaginary time circle corresponding to the thermal statistical problem. And what you'd have been led to do is you'd have filled the imaginary time circle at high temperatures anyway by a Euclidean cigar that would be the Euclidean black hole. We're not asking that question because we've taken this Euclidean time circle and broken it up with a Lorentzian evolution in forward and backwards. So in the boundary, I have my imaginary time circle, which has been sort of split up into Lorentzian evolution. So I apologize for the drawing because this is Lorentzian time. This circle should have been off plane to indicate that it's not in the Lorentzian time direction. The claim is you can get this by taking two copies of the black hole geometry, where each copy corresponds to, one copy corresponds to the forward evolution, the other copy corresponds to the backward evolution. So this is the bra part, ket part, and this is the bra part. And you only keep the future half of the outer domain of outer communication of each black hole. So none of this external region, it's not the thermofield double construction. You don't keep the second boundary, nor do you keep any region near the singularity. So the statement is, as you come in to the horizon of the first side of the ket side, you fold over and emerge back on the second sheet, which is the bra part of the geometry. Okay, and that's what I've tried to indicate qualitatively in this picture, where my geometric picture is such that I have a two-sheeted geometry where I just smoothly have a horizon cap and I just go around the horizon and come back. This is important for the following reason. There is no contribution from near singularity regions or other asymptopia in this problem for the purpose of computing correlation functions. So a much better way to say it is as follows. I can just, for this particular example, I can just give you a simple coordinatization of a complex geometry. So you take the black hole space-time in ingoing coordinates and analytically continue the radial coordinate to a complex coordinate. This coordinate zeta starts out its life as a tortoise coordinate, but I have put in some phases here to make zeta have unit monodromy as I go around the horizon. So the radial direction of the black hole space-time with ingoing time coordinate has been made complex. There's a branch cut running from the horizon out to the boundary, and what I'm interested in is a contour that encircles the branch cut and comes out. So I could just give you a simple contour integral prescription for computing correlation functions on this complexified geometry, which is what we are calling GRSK geometry, as was proposed by these folks I mentioned. Okay. So here's the explicit metric in complex coordinates. Here's the explicit tortoise coordinate, and all we need to do, all I'm assuming is that I have normalized things so that as I go around the cut, the zeta coordinate, which is purely imaginary, it's purely imaginary in the bra part, picks up 1 unit of real part, 1 unit of monodromy as you come out into the ket part. So that's the convention that I'll work with. The second claim, and this is something we proved in the first paper, that all the real-time correlation functions of interest you can compute by just using the standard Gapser-Klebanov-Polyakov-Witten rules or Witten diagrams on this geometry. Okay, so you just fix boundary conditions here and here, compute the correlation functions along this graph. So let me give you an example, and this is sort of simple example. This is the analog of the Brownian problem now. So this would be something that sort of answers Nima's earlier question. So you could imagine now coupling a scalar field to some scalar operator of the thermal plasma. So in N equals 4, we can take some scalar operator like trace f squared and ask what can I read off for this effective field theory of a probe that couples to trace f squared. Well, we know that the trace f squared is dual to a bulk scalar field. In fact, it's dual to a bulk master scalar field. But in general, if I take a conformal operator of dimension delta, I want to study the dynamics of the dual operator, which is some phi in the bulk theory, in this GRSK geometry. I have chosen ingoing coordinates. So the time reversal symmetry of the Schwarzschild of the thermal state is broken, but the geometry manifests it by a Z2 involution, which shifts the ingoing time by this imaginary tortoise coordinate shifted by this in my initial ingoing time. So for technical reasons, it's actually convenient to work in a basis that's adapted to this involution. So these details are not fully important except for one purpose, which I will tell you. It makes life easier to solve in terms of solving the problem. So what you do is you solve the problem in the bulk for any field you want with ingoing boundary conditions on one copy of the geometry. So for that, you don't need to know all these complex details. You could just pick, say, this part of the geometry and solve for the usual ingoing boundary scalar field problem. And that would mean just some field that's falling in through the horizon. We know such ingoing problems are characterized by quasi-normal modes. So that is the physics of retarded response associated with black holes. So my algorithm is to say, compute the ingoing Green's function, ingoing boundary to bulk Green's function with some suitable regularity conditions, normalization at infinity, and suitable regularity, ingoing regularity conditions at the horizon. And it's easy to work, it's simplest to work in Fourier domain, where you can compute these things directly. What ingoing means is pretty clear if you work in ingoing in Fourier domain. Having done that, use this Z2 time reversal involution to figure out what the outgoing solution is. Okay. The fun thing is that there's a nice conjugation symmetry on the solution space that allows us to write down the outgoing solution in terms of the ingoing solution. Once you have the ingoing and outgoing solutions, you can write down the general solution, but characterized by both these Green's functions and boundary values on the two boundaries. So J's are basically sources for the operator for the field phi, dual to my operator say trace f squared on the two boundaries of this geometry. So unlike the usual GKPW dictionary, which is where I have a single boundary and I have one set of sources, I now have two boundaries, one at this end of the contour and another at this end of the contour. So I need to give you sources here and here. And instead of working with the right-left sources, I just have switched variables to work with these average difference sources. The average and difference, I remind you, are sums of right plus left over 2, and difference is right minus left. This factor, which comes from the which comes because of the monodromy that you pick up as you go around the branch cut, beautifully translates into thermal factors which are necessary for the black hole geometry to give you Green's functions that obey thermal characteristics. Okay, so in fact, I could write down the solution as the ingoing Green's function plus a combination which I would call the Hawking Green's function, which is related to a particular combination of ingoing and outgoing stuff. And you see already at the level of Green's function that if you didn't know about Hawking radiation, if you hadn't sort of studied quantum fields in black hole backgrounds, you can derive this from this prescription. But this is sort of post facto because we knew this already for 5 decades now. And it's completely key in the way the problem is set up and the way the geometry works that all the statistical factors work out correctly. I'm only talking about bosons. Other people have discussed fermions and systems with chemical potentials where you will have appropriate dressing of the statistical factors. If you compute these bulk to boundary propagators, or if you want to compute exchange diagrams, you compute bulk to bulk propagators. Any correlation function you want to compute of these boundary sources is simply some kind of cut integral, a discontinuity integral on one copy. Okay, this is something we proved. So you can show that all the correlators are computed by some contour integral in the zeta coordinate, but that can be essentially mapped to an integral of a discontinuity from the horizon to the boundary. So this is the prescription that was originally argued for without in the early days of real-time ADS-CFT by Son and Starinet, but I claim that this provides a consistent derivation of that statement from first principles. Any questions so far? Okay. So now I'm just going to tell you some various results. I'm not going to show you how we got them, but so I'll tell you some results in the context of probes which are forgetful. Okay, so which I'll call Markovian probes. So this is related to your question, Nima. So now let me just play this game in ADS3. where I'm thinking of a 2D CFT, where I'm taking correlation functions of operators of dimension delta. These are universal. They don't need to know anything about central charges on the cylinder. They're just given by conformal mapping. So here's the answer that you can compute directly, either from CFT techniques or from studying the physics in BTZ geometry with this story, in terms of the dimension. And the only difference is that these answers are written in Fourier domain. They're written after Fourier transforming on the plane in terms of frequencies and momentum. So this is the 2-point function OA/OD. I'm writing things in terms of 2-point functions because what I actually compute is the generating function of correlators with sources set up on the boundary using usual GKPW, and then vary that to get 2-point functions. This guy is the retarded correlator, and OD correlator is the fluctuation. And I've written the answer in a particular way, emphasizing that the average difference correlator is related to the difference correlator with a statistical factor, with signs and statistical factors dictated by fluctuation, dissipation, cleavage. So this is not an accident. This is what it needs to be from first principles in thermal field theory, and the black hole geometry reproduces that. Of course, this statement was known. This was first computed by Son and Starinets. This statement is not a surprise, but it's nice to see that work out from the geometry. We also did compute some 3-point functions. They're a bit messier. They're infinite sums of hypergeometric functions in this way of writing, but you can write them down. You can do similar calculations in higher dimensions, but there you encounter an interesting catch. The interesting catch is that wave equations in black hole geometries are not analytically solvable, but we can make progress by working in the low frequency, low momentum regime in units of temperature, and we can solve the equations order by order in perturbation theory in beta omega and beta k. When you do that, you can translate the answers into an effective stochastic field theory of the probes. It works exactly like the Langemann problem, except that now it's a quantum field theory with nonlinearity, so there's non-Gaussian interactions in the theory. And for the kind of couplings I showed you, this is our general prediction for endpoint contact interactions in the bulk. And you can check that the various dissipative coefficients, and which are basically the coefficients of dA. There's a psi A missing here. And dd, which is the fluctuation coefficient, they're related by the standard fluctuation dissipation relation at linear order, at Gaussian order, but we also get non-linear, non-Gaussian fluctuation dissipation relations. These are new predictions that come from holography. I'm not telling you what these coefficients are. Yes, Nima.
Is there, I'm sort of trying to understand this small beta omega beta k regime. So yeah. Beta is sort of the inverse temperature, which is sort of the scale, the time scale associated with your environment.
Correct.
It's the thermal environment.
Correct.
And can I interpret this as some sort of a comparison between time scales of the Hamiltonian of the system versus the Hamiltonian of the environment?
Yes. So what I'm asking is, it's the same statement as in effective field theory. So we want to ask about, so all time scales in these holographic environments are order the thermal scale. So they're all set by beta. So you can ask how probes behave when on time scales that are small compared to those thermal time scales, or spatial variations which are small compared to those thermal wavelengths.
Yeah.
So that's the case. That's the case here, and that question makes perfect sense for the kind of probes that when the probe couples to the environment operator, that falls through the horizon and decays away on thermal scales.
Yeah.
Okay, so this is still the Markovian regime that you mentioned at the very beginning.
Yeah, I guess that's what I was trying to understand. Whether am I allowed to interpret higher orders in beta, omega, beta k as non-Markovian, like order by order becoming more and more non-Markovian?
No.
No,
I think the order of limits is that beta. So if you take beta omega of order 1, that would be the regime where I have to keep track of other things. So here I'm trying to integrate out the environment. The environment cutoff scale comes with T. So any frequency and omega smaller than T is in my effective field theory.
All right. Sorry. Yes. Yeah.
Okay. But you have an important point, which is that not all operators are Markovian. So black holes can have memory, and especially ADS black holes have memory. And the reason is the following. I'll phrase this in the language of quasinormal modes. Most quasinormal modes have frequencies that are gapped in units of temperature. So if I trace f squared, the operator in n equals for Super-Yang-Mills, which is dual to some massless scalar, that guy has its lightest quasinormal mode is only excited at the scale of temperature. So any probe that I use to probe the system with, which doesn't get to those thermal scales, is completely fine. It can be understood in effective field theory. But there are dangerous operators which usually correspond to conserved currents. They're not necessarily conserved current, but they usually correspond to conserved currents. And for example, if you look at the stress tensor, then there's an operator, then there's a mode which is very long-lived. It's long-lived, and if you in fact compute the thermal 2-point functionals of this particular of the time-space component of the stress tensor, that guy has a diffusion pole. So this is the origin of hydrodynamics in the context of ADS black holes. So you have modes that correspond to momentum diffusion, or you have modes that correspond to sound propagation, where there are quasinormal modes which go to zero as frequency whose frequency goes to zero as momentum goes to zero. And this was, of course, pointed out almost 2 decades ago in his beautiful work by Polycastro-Son and Starinas. So now, if you try to couple to such conserved currents of your system, of your environment, and then try to integrate out the environment, you will get something absolutely non-local. Because there's long-lived effects, there's essential non-Markovian physics coming from the fact that there is long time and high long distance behavior in these modes. These guys carry memory. So the way to think about this is in the usual language of effective field theory. You should think of these long-lived quasi-normal modes as Goldstone modes or moduli. Unlike in Wilsonian effective field theory, you should not try to integrate these out, but rather retain them as Goldstone fields in your effective field theory. So the question is there a Wilsonian theory that retains these moduli and keeps track of this long-lived behavior, so that you can write down some local effective field theory of these variables? Okay, this question was not answered till recently, and I'll tell you the answer is yes. But before that, I need to tell you one technical statement, because the technical statement helps understand the answer. So let me tell you this technical statement in a very simple context, by not talking about energy momentum tensor, which is a bit complicated, but just talking about a conserved global current, which is an abelian current. So this current in the boundary field theory corresponds to bulk Maxwell field. The coupling is between operator and sources. Okay. J is a current operator, and mu, the boundary value of this bulk Maxwell field, is a source for this current operator. I can decompose this gauge field into harmonics in the following way. I'm thinking of conformal field theories on the plane. So I pick a direction of momentum propagation. So I pick some direction, let's call it the x direction, where moment, which is the direction along which momentum is going. And then I decompose every mode in spherical, in planar harmonics in the plane perpendicular to this momentum mode. So if I take, for example, a vector field, the little group is SOD minus 2 in ADS D plus 1. A vector field expands in either scalar harmonics or vector harmonics. And it turns out, if you count the number of degrees of freedom, there are D minus 1 degrees of freedom in the current, because the current satisfies one conservation law, d mu j mu is 0. So that d components of a vector with one conservation law, so that exactly d minus 1 degrees of freedom. But d minus 2 of those are short-lived. They're Markovian. They're physical photons of the bulk that just fall inside the black hole and decay away in short timescales, in thermal timescales. 1 degree of freedom is long-lived and corresponds to charge diffusion. Okay, so we have a problem, and the problem is in that the current operator itself is not en masse either non-Markovian or Markovian. It has a piece which is non-Markovian and a piece which is Markovian. So you need to separate these out ab initio. If you don't, your effective field theory has mixing between these guys. So if you want to do something Wilsonian, you want to keep track of what are fast modes and what are slow modes, and write down effective field theory separately, keep for both of them. So same thing is true for energy momentum tensor. It also contains Markovian and non-Markovian modes. The second problem, which has to do with the fact that this is all in dynamical gravitational theories in ADS-CFT, that conservation of the boundary currents in the bulk is a constraint equation, is a Gauss constraint equation. And in particular, the radial gauge constraint tells us that a difference current is always on shell. Okay. So this is a problem. This is a technical problem for those of who you've thought about this problem in the context of ADS-CFT. Most people, when confronted with this problem, impose a gauge condition which chooses a radial gauge. This radial gauge is a disaster because of this one component of this current being on shell. So you can't take the difference current, put the difference current on shell and keep the average current off shell. That doesn't make any sense. So people who attempted this problem before, including the paper I mentioned, had to posit some rules to try to get this guy off shell by working in, because they tried insisting on working in radial gauge. We're not going to do that. Okay. We're going to be agnostic and ask how to package everything in terms of gauge invariant degrees of freedom that makes the separation between Markovian and non-Markovian degrees of freedom manifest from the get-go. The amazing miracle is that gravity works and it tells you exactly what to do if you ask it the right question the right way. So claim, if you take this harmonic decomposition seriously, you can repackage the entire discussion of this Maxwell field in a very simple way in terms of a couple of scalar fields. I'll tell you what the word designer means in a second. So the Maxwell field dynamics splits up into a decoupled, at the quadratic level, into a decoupled dynamics of a single scalar field, which corresponds to diffusion, and d minus 2 scalar fields, which correspond to photon, charge propagation. And I'm going to call them 5 designer fields because they're characterized by an index m, and the index m enters the wave equation in the following way. And it might be a bit clearer if I write down what the index says. If you do the gauge invariant decomposition, Markovian and non-Markovian fields decouple at the Gaussian order, at the level of kinetic terms, the bulk. And you can package every such degree of freedom into the dynamics of probe scalar fields in the bulk, black hole geometry, where these scalar fields are not minimally coupled to the background. If this factor was 0, if this factor was 1, this e to the chi was 1, then it would be the usually minimally coupled scalar. But there's a dilatonic coupling with some auxiliary dilaton, which modulates how these scalars behave in the gravitational theory. What is this dilaton doing? If your field is Markovian, if it has only short-lived modes, then this dilaton grows steeply towards the boundary of ADS. It's some power law typically, and that's how I define this index M. Then it prevents these fields from getting to the boundary of ADS even better than ADS asymptotics. So ADS, remember, is a box. So think fields don't want to, physical fields don't want to go out to the boundary. They have some power law behavior. But if I make that power law even steeper, the fields just want to fall into the horizon. Their lifetimes become shorter, which is nice for the purposes of thinking of Markovian physics. But these non-Markovian guys, like charge diffusion, sound propagation, etc., they do exactly the opposite. They are floppy near the boundary. They might be strongly coupled somewhere near the horizon, inside the horizon, but that doesn't matter because our geometry only is capped off near the horizon. But because they're floppy near the boundary, they hover near the boundary for a long time. And this is the feature that you're really looking for, because what you're after is to isolate the modes that don't fall into the black hole. Because if they fell into the black hole, then you'll be able to integrate them out. Because they don't fall into the black hole, you can't integrate them out. You want to write down the Wilsonian theory for it. Okay, and it's the statement that comes out of various calculations that modes with behavior of this kind are Markovian, and modes with behavior of this kind are non-Markovian. And you can characterize this in terms of the single index, this Markovianity index. And I can tell you the answers quickly for gravitons. Transverse traceless tensors are Markovian. There are some number of them. Transverse vectors are non-Markovian, but they have a particular index and correspond to diffusion. And the scalar modes are non-Markovian, corresponding to sound propagation with a different Markovianity index. Something even more amazing is that if you compute the gravitational action for this decomposition, the Gibbons-Hawking and the counter terms basically tell you how to quantize these guys. They tell you that to compute correlation functions, you should quantize Markovian modes with standard Dirichlet boundary conditions, but you should quantize non-Markovian guys with Neumann boundary conditions. But I don't want to compute correlation functions. I want to keep the non-Markovian guys as fields. So I should just do a Legendre transform and convert this Neumann boundary condition to a Dirichlet boundary condition to compute the Wilsonian effective action.
Sorry, Mukund, can you say that again? So why is that Markovian have to be Dirichlet and non-Markovian have to be
Neumann? Yeah. So the basic boundary conditions are set by this action.
Yes.
The boundary matrix has Dirichlet boundary conditions because of the Gibbons-Hawking term.
Right.
Now I can ask what happens when I plug in my ansatz. I have a particular harmonic decomposition of these modes. I haven't told you how I got these modes, what these modes are built out of. But it turns out that when I do the decomposition, there are derivatives in writing my metric field in terms of these transverse vectors. The derivatives work out in a fashion to do the following, that the effective action for these scalars that correspond to transverse vector degrees of freedom, or the scalars that correspond to this sound mode, their dynamics is such that, instead of getting the standard, if you get an action of the following kind, this Lagrangian you would quantize with Dirichlet boundary conditions.
Sure.
But if I get an action with this boundary term, then this says that I'm stationarity implies that I have to quantize it with Neumann boundary conditions. Okay, I might be getting my signs wrong. There's a factor of 2 as well. Because this guy will give you a pi delta phi under variations.
Yes, yeah, right.
And I have to swap that out when I have say additional term here.
Right.
Okay. And I'm making this is an observation that comes out of a calculation that the change of variables to these effective designer fields comes with such boundary terms. So it's not something we are putting in by hand. It's something that comes out of this calculation. Various authors have studied this change of variable, this decomposition at the level of equations of motion. Okay, this is not new to us. This is some ancient thing that people have done over many years. But we seem to be the first people to have asked, what is the dynamics coming from here when you substitute those into the action? And I'm claiming that for the purposes of computing correlation functions, the standard GKPW dictionary, Markovian modes come with Neumann Dirichlet boundary conditions. Non-Markovian modes come with Neumann boundary conditions. There's a small ambiguity. There's small ambiguity in this window between -1 and +1, but that's like standard versus alternate boundary conditions.
Right.
Okay. So I won't belabor the point. There's something similar is true for gravitons coupled to gauge fields. That's, as you can imagine, much more complicated. But the quantization is exactly what I said. For Markovian fields, we fix sources on the right and left boundaries, and we evaluate the generating function of correlators. This is the standard problem I showed you, and that's what I showed you the answers for earlier. For the non-Markovian modes, because these solutions are floppy near the boundary, they blow up near the boundary. They actually have power law divergences near the boundary. So what is usually, why that is case is because we are integrating out moduli, and we're trying to compute the 1pi generating function for correlators, and the 1pi generating function is just not local. So it's divergent because the 1pi generating function is the wrong thing to compute. But what you should compute is Legendre transforms this generating function to a Wilsonian object, parameterized by expectation values of boundary fields. Instead of parameterizing the answer in terms of boundary sources, parameterize the answer in terms of boundary fields. And that's easily done, and you can just solve the problem. There's even a fun fact that you can actually repurpose solutions for the Markovian guys in terms of non-Markovian guys, because there's some nice analytic continuation in this Markovianity index. And the claim, and I'll end in 2 minutes, is that what you should compute is a boundary Wilsonian influence functional, where you prescribe sources for the Markovian part of the operators and waves for the non-Markovian part of the operators, because you treat these as moduli and you keep them in your effective action. And at the Gaussian order, which is what we've been computing in various examples, we get a structure that's pretty much dictated by fluctuation dissipation. We get a structure for the Markovian piece and a structure for the non-Markovian piece. In the Markovian piece, this kernel is actually a Green's function. In the non-Markovian piece, this kernel, like with any dynamical objects, it's an inverse Green's function. So this has solutions, on-shell solutions. When you invert it, it gives you poles in the propagator, the diffusion pole and sound pole of hydrodynamics. And with Julio, we are working out some non-Gaussian effects in some toy models, because we want to understand the structure before we actually compute vertices in gravity, which is a bit more work than computing fluctuations around given solution. Anyway, so I'm almost done, but I can just flash for you the general structure that we get a piece which is for hydrodynamics. If you're coupling your probe to the stress tensor, you get something that's related to the ideal fluid, because the background free energy is that of an ideal fluid of a black hole. Then you get the Markovian tensor modes, non-Markovian momentum diffusion modes, and the sound mode. And I've written down the propagators for you, and the propagators and inverse propagators for you in n equals 4 superangles. And many of these expressions have been known in literature. They're just been computed in very different way in this discussion. Okay, so to summarize, I claim that holography actually provides us with a very useful way of thinking about open effective field theories. I think there's a lot more to be done here, and we could ask more interesting questions, both in the context of ADS-CFT and other generalizations. Maybe think about things like what Nima was asking about quenches, etc., etc. But we've only looked at equilibrium problems. And the message I want you to take away is that thinking about these problems in gravity is actually quite nice, because semi-classical gravity helps to disambiguate long-lived and short-lived modes much better than thinking about the problem directly in terms of field theory. This problem has been considered by various people in field theory, and there's various statements in hydrodynamic literature, primarily coming from the fact that the 1pi effective action for hydrodynamics makes no sense from loop effects. But our statement is, why would you compute the 1pi effective action? Just compute the Wilsonian gadget. And I think one can study non-Gaussian features, etc., etc. And I've just outlined a bunch of things that one can consider in the future. Thanks.
Thank you so much, Mukund. Are there any questions here or online?
Can I ask one question?
Yeah.
So I think you mentioned about quantum channels in the beginning of the talk. Which one is quantum channel in this story?
Oh, I mentioned quantum channels at the beginning of the talk. So the way I'm thinking about this problem is, if you have, say, for example, in this last guy I wrote here, if you have a coupling between some n equals 4 super-Young Mills plasma and some operator built out of this scalar field psi, let's say tensor operator built out of scalar field psi. And I start out my system where the scalar field is in the vacuum state and n equals 4 super-Young Mills is in the thermal state.
Okay.
So I claim that the way you should run this problem is you should integrate out the n equals 4 plasma and write down the effective field theory of the scalar field psi.
Okay, okay, I see.
So that would give you the quantum channel that tells you how the state of the psi state evolves as a function of time. So people would say there's some Lindblad operator that encodes the effective non-unitary description, but I don't want to use that language. I just say it's some quantum channel that tells you how the zero ket zero brass state evolves in the psi theory.
You actually don't. You're unsure if there's a Lindblad approximation, right? Because it's a quantum channel, but
Yes.
it takes further approximations to get Lindblad or something.
Correct. That's why I'm not saying there's a Lindblad operator. Yeah.
Any other questions?
I have one more question.
Mhm.
So in the beginning, I mean, throughout this story, you are constructing density matrix which has like R degrees of freedom and L degrees of freedom, and you said those equal to Brownian ket sort of.
Yeah.
So my question is, what is the structure of a Hilbert space in this case? So, yeah.
You can think, if it's a finite dimensional system, you can think of the Hilbert space. You can think of it. See, a density operator is a linear operator that acts on the Hilbert space. It doesn't live in the Hilbert space.
Okay.
But I can use I can think of this as a state vector in H tensor H star.
Okay.
So that's the structure of the Hilbert space I'm using.
That's what I would think about it. Absolutely, yeah.
So what is H star?
The conjugate basis, the conjugate Hilbert space.
Commutant.
CPT conjugate Hilbert space.
Okay, yeah. So now then the next question I have is, are you assuming some kind of factorization of Hilbert space in this calculation?
I am implicitly using those words, but at the way I'm running, so you're right that technically, since I'm talking about thermal field theories in non-compact volume, no such thing exists. But at the level of effective field theories, which is all I'm caring about in terms of couplings, I think I don't have to use those words to do the calculation.
Okay. Thank you.
Yeah. So indeed, I think if you actually want me to answer what the quantum channel is, I think I have to use a language that you guys are more familiar with in terms of operator algebras. But that's not what I'm trying to. That's not the goal of this discussion. It's to write down these effective field theories of plasmas.
Thank you.
Any other questions? There are no questions online. Let's check. Okay. If not, let's thank Mukund again for the wonderful talk.
Thanks, Nima.
Thank you so much. Thank you. All right. Have a wonderful day.
You too. See you guys.